Welcome to my presentation, Visualizing Differential Expression Data with FlowSets. My name is Felix Offensperger and I'm from the Bioinformatics department at the LMU Munich. More and more multi-omic, large and differential expression data sets are generated and available. Scattered analysis or pairwise comparisons are difficult to interpret and make it challenging to identify and understand underlying processes. But differential analysis of large-scale expression datasets are crucial to derive disease pathways and condition-specific causes. Here, our goal is to make a flexible analysis of multi-differential datasets. Here we introduce FlowSets. FlowSets make it easy to get an overview of many conditions. Here on the x-axis. With FlowSets, many types of data can be represented, and therefore also different types of conditions. Here called more technically states. Within each condition, features, for instance genes, can have different expression levels, which are categorized in classes. Classes can represent expression values, fold changes, or any other type of input, which is before categorized. FlowSets visualizes the change of features between those states. Since we want to categorize continuous expression values, finding reliable thresholds is problematic. We opted for representing genes in multiple categories using the well-studied concept of fuzzy theory. This way we avoid the problem of thresholding pretty much, and are able to represent rather inexact measurements in an easily understandable way. We take our input values, here for example fold changes, and assign them to fuzzy variables. Here, for fold changes, we normally speak about downregulation, neutral, or upregulation. A fold change of 0.6 is normally regarded as slightly upregulated. We assign it to up with 0.6, neutral with 0.4, and down with 0 membership. We now show the transition of fuzzy values as flows. For a given feature, each node holds the membership of the feature at given state and class. As our example on the fuzzification, a fold change of 0.6 is with 0.6 in the upregulated class and 0.4 in the neutral class. In the next state, the feature is with 0.9 in the upregulated class and 0.1 in the neutral class. To get the weight for one transition between two neighboring classes, we use the dot product. Combining all features and states in FlowSets, we get an overview over the whole regulation in the data. Here the biggest mass is in the neutral class over all states. We now know which membership each feature has in which edge, and we can also track a single feature over the whole FlowSet. After building our FlowSet, we can now perform different types of analysis. One can be interested in features on the left side in the feature-centric analysis, where we select single or multiple features and are interested how does a gene or gene set flow through the FlowSet system, or how do genes in the gene set cluster for a given classification. On the right side, we are more interested in the flow-centric analysis. Here we can have a selection of nodes or edges and inspect which genes follow a specific pattern. What is the membership distribution within a flow? And what is the functional meaning of a flow? So, which gene sets are contained? Analyzing TCGA data of 17 types of cancers and the fold changes between cancer and corresponding healthy tissue, we can now look at the system in FlowSets. Using FlowSets, we identified Cyclic8 as the only gene which is positively associated with kidney cancer. While this finding has already been reported in literature, it is easily checkable with our FlowSet tool. Additionally, we can check if there's any regulation besides the three kidney cancer types, as seen here in the third state, slightly downregulation. Likewise, EGFL6 was already described as a pan-cancer gene, which is made easily understandable using FlowSets. Similarly, we could ask whether there are genes which are primarily expressed in lung cancer. Indeed, such genes exist, like for instance FOXI3, which has already been shown to be involved in metastasis formation. For a gene set overrepresentation performed on the selected FlowSet pattern, we learned that lung cancer is associated with several immune processes. Interestingly, also the IL-22-mediated signaling pathway, which is known to be elevated in lung cancers. These examples show that using FlowSet, it becomes easy to visualize and interpret large-scale data sets, even when comparing different gene expression results. The falsification of the input data makes expression levels, on the one hand, more understandable, but also enables the partial representation of genes or features in these expression classes, and therefore a more detailed analysis. Thank you for your attention.